Hello everyone. For this tutorial video, I would like to explain triple integrals and spherical coordinates, which requires you to carefully plot them out, just like spherical coordinates in general require careful foresight, because of how complicated they are compared to something like cylindrical coordinates. In particular, if we remember when we first studied spherical coordinates, we derived a formula visually for x equals magnitude times sine of phi times cosine of theta, y equals magnitude times sine of phi times sine of theta, and z equals magnitude times cosine of phi, and x squared plus y squared plus z squared equals magnitude squared. We next assume that magnitude must be greater than or equal to 0 at all times, and that phi must be between 0 and pi. If we next choose to integrate specifically on a spherical wedge and no other shape, this means we have further restrictions of magnitude being between a and b, angle between alpha and beta, and phi being between delta and lambda, where delta and lambda do not have the meanings given earlier from previous tutorials, but rather are arbitrary symbols to indicate that we are changing the limits of integration. And we can see from a graph of it, a spherical wedge may sound intimidating at first, but is nothing more than the intersection of a sphere and a cone, somewhat similar to what you see in an ice cream cone with ice cream in it. We will give the proof of this in the next video because it's too complicated in this video, but the formula for the integral and spherical coordinates is change in volume equals magnitude squared times sine of phi times change in magnitude times change in theta times change in phi. So we now substitute this in for change of volume, and substitute in the limits we found for the spherical wedge. So now we do one example, as in evaluate this integral, where the volume is the upper half of the sphere, x squared plus y squared plus z squared equals 1. We see that magnitude is in between 0 and 1, the angle theta is in between 0 and 2 pi, and the angle phi is in between 0 and pi half, owing to how I restricted it to the upper half. So now we plug in the formula for a triple integral in spherical coordinates, as well as plug in the formula for z in terms of spherical coordinates we saw earlier, and then do the integral. Once we do all of our steps for computing integrals from calculus 1 and 2, we get 4 pi as our final answer. Now that we have figured out how to compute triple integrals in spherical coordinates, we can transition from discussing triple integrals specifically to change of variables with any iterated integral, double, triple, or otherwise, as well as give a proof of the change in volume formula for spherical coordinates. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.